and that was sending some sort of signal that said, go into disable, like shut down, and they didn't know why. And they didn't get it resolved in the 5-minute or whatever window, because they do, when they do the countdown, like they hold for 5 minutes and they check everything out, and then they go on and do other countdowns.
The window was 48 seconds.
Okay, well, in that, yeah, so.
So they had no time to check anything. It's either no problems or no launch.
Right. So when they say at the earliest tomorrow, that if it launches tomorrow, it means that they resolved this issue by then.
So, do you know any more about the issue, or?
Is it Brian and the mine there?
I'm not really sure if they're there or if they're in Dulles. Orbital's based in Dulles. They're there. Oh, okay. I was a little confused because Brian was going to Orbital a lot.
No, Brian went Mike.
That's for me.
Yes.
Yeah.
What is it?
Thanks. The ultimate guy for beer.
He complains he can't find good beer anywhere.
Yeah.
I'm like, you haven't been around the city.
Are you still on?
Have you been to Birth Castle? Birth Castle? You say you can't find good
Well,
Between like having the A and
does he not know? I hate the ales, IPAs.
You hate ales? What?
So
Okay,
that's-
don't go to Birth
so
Castle,
that's
it's
why-
Belgian ales.
That's why it's difficult for me to find. I prefer the German ones, like
I've heard you have to. Even does he drink, does this guy drink spice beer?
Schneider. There are a few. There are a few. And it's I really like Radiometer. But that's really back to Yes, but that's outdoor. I mean, they have some small sizes. I mean, those are the screens that I really hate. The moment I see a screen, I just don't go.
No.
Unless they're super event, but I won't be sure. I'm not going.
You ever been there? You go to the Sistine Chapel and there are monks.
Let me just trip over the camera a little bit, right? Thank you.
The patience is very hard.
You have to wait when you brew it to drink it.
Do you need any special conditions for the storage space? Or we just leave it someplace?
They do have some awesome things.
But otherwise,
They should sell
depends
other
on the kind of beer,
to make the
but
beer
it's
become a little more.
comfortable and probably
So you don't really need basement approximate control.
we don't do that. There's some of those styles though have to be kept at cooler temperatures, and that probably but
Well, you will say yeah. But I never really got motivated. Maybe I'll turn alcoholic if I go.
we should have you over next time.
But it's great.
It has a carboy, which is like a 5-gallon glass jug. And then you have, and then you need to have like to brew it in like a metal pot, not like this. And then you need beer bottle.
I think maybe we should start. There's enough people here. So Kirk, I
guess you're going to tell us about Glory? No?
I'm going to talk about the aircraft prototype to
Okay.
Glory.
Okay, great.
Proxy.
Excellent, excellent. Okay, so please tell us about that.
Okay. So the title is Atmospheric Aerosol Optical Property Retrieval with Scanning Polarimeters, which include both the Glory instrument and our airborne prototype. So this is essentially my thesis defense talk in sort of an abridged version. I finished at Columbia in December. Now I'm a postdoc here at GISS doing essentially the same thing. So just to kind of give an outline, I'll describe what aerosols are, how we remotely sense them, and how scanning polarimeters as a type of remote sensing instrument work. A large component of my thesis involved the creation of this piece of software that I call doubling and adding optimization. It's how we retrieve aerosol optical properties from scanning polarimeters. And several chapters of my thesis had to do with an investigation of the ability of scanning polarimeters in several different scenes. I used data from 2 different field campaigns, one called ArcTAS, the other Milagro. And these both became papers that I submitted a couple weeks ago. Actually, this one is now available on ACPD. And then I'll give some conclusions of future work. So I can't imagine that this is a new figure to any of you, but this is from the, in case it's not, this is from the 4th assessment report of the Intergovernmental Panel on Climate Change. This is essentially tallying up the various contributions to anthropogenic contributions to changes in climate. Greenhouse gases are at the top. Aerosols are down here as a potentially negative forcing. And the big deal is that the uncertainties associated with aerosols are on the order of the positive forcing due to carbon dioxide. So this is a kind of unsettling. So the question is, why are aerosols so difficult to both measure and to model appropriately? I'll start by saying that they're very regionally distributed, and their optical properties are highly heterogeneous. As sort of a qualitative proof of this, I'll show an image. These are both from the MODIS instrument. The image at the left is dust blowing off of Libya into the Mediterranean. And the point I want to make here is that even though these are both characterized as dust aerosols, you can very obviously see that they have different optical properties. One is very bright, one is very dark. The other point I want to make is how spatially heterogeneous they are, how regional they are. And this image at the right is the monthly aerosol optical depth from the MODIS instrument for the month of July in 2005. Aerosol optical depth represents the total column extinction in the atmosphere. And you can see that there's some parts of the world where the aerosol optical depth is very, very high. This is Saharan dust here. This is forest fire smoke here. And there's other areas of the world where there's very, very few aerosols. And so this variability spatially is difficult from both the measurement perspective and from the modeling perspective.
How does MODIS see aerosol over land? I thought there was a problem with heterogeneity.
Well, that's why this is black here and here and here.
We've got, there's obviously aerosol to get in the back. So
right, it depends on the type of aerosol. They have an algorithm that they call Deep Blue. And this is something like Christina Su, HSU. And that, I think, uses some more UV channels to try to understand what's there. I don't know if that went into creating this, but I think it's not that they can't observe over land, it's that they can't observe over bright land.
okay.
So, okay, and I'm sure most of you also know this. This is the many different ways in which aerosols can interact with climate. Again, this is from the 4th assessment report of the Intergovernmental Panel on Climate Change. So some of the effects are direct effects of aerosols. They scatter and absorb. They interact with clouds in many different ways, and so on and so forth. So even with the same satellite data set, there are examples of people coming up with very different understandings for the climatological effect of aerosols. I don't mean to pick on either of these authors here, but just as an example, in 2005, they came up with very different numbers for forcing due to aerosols that do not agree within their uncertainties, their stated uncertainties at all. So this is a problem. And problem is really not on the end of modeling. The problem is more on the end of observational capability. Most aerosol observations are underdetermined. In other words, if we want to know what's going on in a situation, we need to know a lot of things about an aerosol. We need to know what's the extinction, the total extinction of the aerosols. We want to know aerosol size and refractive index. Refractive index helps us differentiate different materials, helps us understand absorption and other optical properties. We want to know something about non-sphericity. We want to know something about the way that those aerosols can interact with clouds. And I'm sure people could come up with a list of other things here that we want to know about aerosols to model them appropriately. The problem is that to observe them, we also need to sort of be able to see all of these things at the same time. And in many cases with instruments such as MODIS, we just don't have that much information. So MODIS retrievals need to make a lot of assumptions about, say, surface reflectance or some of these other parameters. The state of the art as it is now essentially observes, for most satellites, observe aerosol optical thickness, usually a proxy for aerosol size, in some cases something related to the absorption. But for the most purposes, satellites need to make a lot of assumptions about what they're observing. So the philosophy that a number of people at GISS have taken is to work with a new type of instrument that we call scanning polarimeters. And the idea is to sacrifice some of the spatial coverage of instruments such as MODIS or MISR, which are imaging devices, and instead observe many more pieces of information about a single piece of real estate, or a much smaller coverage of the globe. So I'll get into describing that in a minute, but just to say that we've been working with two different types of instruments here. The RSP, the Research Scanning Polarimeter, is our airborne instrument. All of the data for my work has been with this particular instrument. RSP is essentially the prototype to the Aerosol Polarimetry Sensor that was supposed to be launched today and has been delayed for 24 hours. So for the most case, you can just say that the one is the same as the other. They're very, very similar characteristics. So they are scanning polarimeters. That means that rather than observing an image, they're observing a very narrow swath. So if you imagine the aircraft is moving in this direction, it's scanning like this as it flies. The point is that for a particular piece of real estate on the ground or in the atmosphere, you're going to have observations at many, many different viewing angles. For the case of the RSP, you have about 150 viewing angles. With APS, it's about 250. So you have observations with a very high angular resolution. We also have observations in 9 channels, everything from 410 nanometers to 2250 nanometers. And this is also something particular to scanning polarimeters, we are sensitive to polarization, or at least the first 3 components of the Stokes polarization vector. What this means is that we're sensitive to total reflectance and the linear polarized component reflectance. So if you're not familiar with Stokes vectors, just to say very quickly, the Stokes vector is one way of describing the polarization that's inherent in a scene. It's done with this 4-element vector that has I, Q, U, and V in it. I represents the total intensity or reflectance, depending on the type of units you're working with. Q and U indicate the direction and magnitude of linear polarization. V indicates the quantity of circular polarization. We don't actually measure V. For various reasons, we believe that the magnitude of V in atmospheric scattering is very small. I typically work with reflectance units, which are computed this way, and I just wanted to say that they can be negative because Q and U are indicating a direction as well. They can be positive or negative values. So I just want to say that if you see a negative reflectance, the sort of intuition that you would use for the reflectance that you would observe it's not the same thing. So it's okay that it's a negative value. So how do our retrievals work? Well, this is an example of an observation from one particular scene. This is over a very thick smoke plume in Canada. The different colors here represent different channels. This is a function of view zenith angles, with different viewing angles. And Q is one component of the Stokes polarization vector in terms of reflectance. So obviously this is not something that we can intuitively convert into an understanding of what sort of aerosols are there. So what we have to do instead is match a radiative transfer model to our observations. In fact, that's actually what's been done in this particular plot. It's a little fuzzy to see here, but these lines that are sort of dash black and then the color dashed are the model fit to that. So whatever model we can fit to our observations, the parameters that went into creating that model are what we retrieve from our scene. We say, well, it's consistent with observations, so that's what we think is there. So just to describe very briefly the types of parameters that we include in our radiative transfer model, we want to know something about size distribution, sort of mean and width of the size mode. We want to know the complex refractive index. The real component of the refractive index is going to tell us something about the type of aerosol. The imaginary component is going to tell us something about the absorption of that particle. We want to know the number concentration, how much is there. Typically we do this for two different size modes, a fine mode and a coarse mode. Well, I guess I don't really have time to get into it, but generally in the atmosphere there are two different size modes of aerosols that are present. Fine mode particles are usually due to chemical reactions, or they're there for chemical purposes. Coarse mode aerosols are typically physically created, such as dust or sea salt. Now, from all of these parameters, we can typically, yes?
With all those parameters, do you worry about uniqueness?
Yes.
Okay.
So I'll get into it later on, but the point with this sort of work is to try to assess what are we independently sensitive to, what's the relationship between different parameters, and it's something that I'm actually going to get into later on. But anyway, the point that I want to say though is that from these sort of core inherent optical properties, we can derive other optical properties which are typically retrieved by other types of instruments, specifically the aerosol thickness or the single scattering albedo. We can come up with all those numbers based on our inherent parameters. So this is what my optimal estimation software looks like. It's sort of a flow chart. I'm going to go through this step by step, so I know it looks a little kind of confusing, but essentially what we're doing is fitting a radiative transfer model, which I'm going to call a forward function, G, to our observations, which I'm going to call by the specter Y. Once we've, in other words, we're trying to minimize the cost function, the difference between our observations and the output of our radiative transfer model, and we're going to take into account error in our observations. So this value here is what we're trying to minimize. So my thesis was the creation of software to do this. I called it doubling and adding optimization. The engine, the radiative transfer engine that I used was a doubling and adding technique, and I optimized it. So what we first do is we make a guess of the aerosol inherent optical properties, the size, refractive index, everything I described a couple slides ago. And I'm going to put that into a vector that I call XA here. This I'm going to insert into our radiative transfer model, which has sort of two components. First, it computes single scattering properties. So given these initial properties, it computes the angular scattering, or the phase functions, for those particles, be they spheres or spheroids. And then I take those results and I put them into a full multiple scattering radiative transfer model, a doubling and adding model, to come up with what we expect to observe at the location of our aircraft or the satellite. For spheres, Lorentz mean theory uses or comes up with the extinction, absorption, and scattering as a function of angle, given particle size and complex refractive index. This is something that we can do exactly. The doubling and adding code then takes the output from our single scattering computations, computes multiple scattering and the reflectances at observational geometry, given single scattering from Lorentz mean, the aerosol quantity, vertical distribution, and other parameters inherent to our scenes, such as surface reflectance. So we have an initial value, it produces an output y, which looks like it's a simulated observation. So then we say, okay, we take our actual observation, which we're going to call y star here, we compare the two, and we ask the question, do y and y star agree? I also take...
Sorry. The observation you mentioned that also takes into account certain assumptions concerning the particle nature, right?
Mm-hmm.
How does that relate to the XA function that you had for the model
Well, okay, so there's two ways you can go about it. You can assume that your model is a perfect representation, which of course is not the case. Or you can think about error and try to simulate the error due to those assumptions when comparing these two. Okay, you have your model error. So in my actual code, I haven't done that. Just an approximation that I'm making that I'm doing correct model approximations. But typically what happens is you take that into account when you're comparing the two. So that would become a part of my error covariance matrix that I'm calling CT here. So what we do is we compare the two, we take our expected error into account, and we say, all right, are they the same? If they are, then the parameters that went into creating that are retrieval. If they are not, then we need to somehow decide how to modify our parameters, rerun our radiative transfer model, and keep repeating this until we can find a match. The logic that we use to both decide if the match is appropriate and to modify our parameters uses the so-called Levenberg-Marquardt optimization technique. I'm not going to get into that, but just to say that, oh, I did put a slide in. Okay, so this is intended for nonlinear optimizations such as this. It involves the computation of this Jacobian matrix right here. I'm going to just get into why we do this later on, but the Jacobian essentially is a way of understanding our sensitivity of our radiative transfer model to perturbations in our state vector, in our parameters. So this Jacobian is useful both for Levenberg-Marquardt, and then at the end we can use it to come up with an error estimate for our retrieval. So if we start out with an error of our observations, this error covariance matrix CT here, we can use the Jacobian matrix to project that error into parameter space. Essentially, this is saying that we have an estimate of the error in our retrieval, assuming that we have an accurate estimate of our observational error and our model error.
How big is your code?
It's the number of elements long of our observation vector y, or yeah, it's big.
Yeah.
So 8,000 by 8,000 or something like that. So, so to summarize, DAO, this software created, computes aerosol properties given RSP observations. This is not the algorithm that Glory is going to use. Primary reason for that is it's slow. So the idea here is that we have a very flexible and sort of in-depth way of doing a retrieval from our observations, and we can play around with what sort of assumptions we want to make about the model, what sort of assumptions, how many parameters we want to retrieve, and so on and so forth. DAO is written to be very flexible in that sense. So what we can do then is use it to try to understand what scenarios are we going to be able to do a good retrieval, and what scenarios are we going to be a little bit more limited. So I did just that. I looked at two particular scenes that are not, they're not sort of typical scenes we expect to do with APS. In fact, a lot of that work is assessment of our capability in more typical scenes has already been done by people like Yesek. So aerosol retrievals over the ocean, that's something that's pretty well established. Aerosol retrievals over land, we have a methodology for it. So I looked into scenarios where maybe we don't think we can do as well. So I looked at two scenes, one from the ArcTAS field campaign and one from the Milagro field campaign, and I'll go into those right now. So the first case study is of a very dense smoke plume that we measured during the Arctic research of the composition of the troposphere from aircraft and satellites field campaign. We were based in Yellowknife, Canada in the summer of 2008 and looked at some very, very thick, optically thick smoke plumes. The issue that we wanted to get to with this field campaign was trying to untangle the vertical distribution of aerosols and the absorption of those aerosols. Somebody said something about being able to independently retrieve parameters. One thing that we think that we can't independently retrieve is both the vertical distribution of the aerosols and the absorption of those aerosols. So what we wanted to do with this field campaign was try to do a number of retrievals just that way, without any external information, and see how accurately we can do it, and then combine our retrievals with data from a LiDAR. Our particular aircraft, which had the polarimeter, also had LiDAR, which gave us a vertical profile of the aerosols. So we wanted to see if that additional information helps us better retrieve aerosol properties. The implication here is that Glory, which is going to be in the A train, is going to be very close to the Calypso LiDAR, which could potentially do the same thing for APS retrievals. So here's what the scene looked like. This is big images from MODIS. This is a very recent smoke fire. It had only been burning for about a day. About, I guess, an hour and a half or so downwind, we overflew the smoke plume. RSP locations or data are in these white little hash marks right here. This red line was the flight track of another aircraft. So we were flying above the smoke plume. This P3 aircraft was flying in the smoke and had a number of in situ observational or observation instruments. So they were measuring optical properties in the plume that we can use as a validation for our retrievals. So just to sort of talk about the scene, the data we have to work with, we used 6 of the RSP polarized channels. We also used 1 of the reflectance channel. And we have about 75 angular observations from 20 degrees forward to 20 degrees backwards. So there's a total number of 525 observations here. So the error clearance matrix in this case would be 525 by 525. Some of the model assumptions that we're making are that, for example, the aerosols are very, very optically thick. This allows us to use the total reflectance at 410 without having to specify the surface reflectance at that band. That the complex refractive index for the aerosols are spectrally constant, and our aerosols are spheres. I can go into my reasoning for all of these assumptions if you want to, but just to move on anyway. So what we're going to do is test aerosol retrievals with and without height information and see, do we do better compared to observations from the P3 aircraft that was flying in the field. Oh, okay, so just to sort of say that graphically, I kind of said it already, but we're comparing 2 things. One is a retrieval where these heights of our aerosol layer are specified by the HSRL, which is a LiDAR. And we see, can we do better in this case compared to something that would be more akin to what we would do in an operational sense with APS, and that is to assume the aerosols are fixed to the ground and say pick a layer height and use this height as one of the parameters we're trying to retrieve. So in this case, we're trying to retrieve more parameters, one more parameter than in that case over there. So here's an example of the retrieval for one of those scenes. The solid lines here with the hash marks are the actual observations. The sort of dashed lines are a model fit to those observations. This is for Q reflectance. This is for the total reflectance at 410 nanometers. And you can see, okay, yeah, they look like they match, right? The question is what the parameters that we've retrieved actually are. So this is an average of all of our retrievals with the LiDAR and without the LiDAR. So you can see things like real refractive index. Well, okay, that sort of makes sense. The size of the aerosols are kind of small. This is a relatively low amount of absorption. And this is a very optically thick plume, so 0.7 at 532 nanometers is well above the sort of global average, but it's not a very absorbing aerosol. What's interesting is that there's some differences between the two.
How can you say you don't see the surface with an optical depth of less than 1? I don't understand.
Well, that's why we're using just the 410. I didn't explain that very well. So this is optical depth at 532 nanometers, but the optical depth is very, very spectrally dependent. So at 410 nanometers, it's something like 1.8 or something like that. And at that case, when the surface reflectance is very, very small anyway, which is what it usually is for a boreal sort of scene, no matter how you characterize what that surface reflectance is, it's not going to really have any effect on the observation. That's why we only use the 410 and not the other channels. So the retrievals are different. There's more absorption in this case. These are smaller particles. So why?
What are the units on the number concentration?
It's number of particles per square micron.
Okay.
So because it's a column measurement, right? So it's not cubed. You with me?
Yes, kind of.
So there's different optical parameters that describe these two retrievals. They come up with very similar optical depths, which is interesting. And I guess the question then begs is, well, how do we compare to the in situ observations? So this is kind of a complex plot, but it's sort of the core of this work. At the very top here, so this is a function of latitude down at the x-axis. So this is the observations as we're flying from north to south across the plume. You could also put this in terms of time or something like that. The image in the top plot is from the LiDAR instrument, so you can see, this is the amount of backscatter. So you can see that our aerosol layer is capped at about, what is that, 4,000 meters here. And the highest amounts of aerosols or backscatter are towards the top of the plume, and the quantity is somewhat variable throughout the plume. This white dashed line here is the retrieved height of the aerosols when we didn't use LiDAR information. As you recall, one of the parameters that we allowed to vary was the height of the aerosol layer. And you can see here that this doesn't really match with reality at all. However, if you compare observations with the LiDAR, which is what's in, which is what's in red, to observations without the LiDAR, which is what's in black, they're very, very similar, and they agree very well with their uncertainty bars, and they also agree very well with this blue line here, or these blue observations, which is an in situ observation made from the aircraft. So these agree very, very well. But then when you start looking at things like single scattering albedo, this is right here, green is in situ observation from the aircraft. Red, again, is when we're using the LiDAR, so we can see we agree generally pretty well. Black is when we're not using the LiDAR, and this is where something interesting starts to happen. In some cases of our retrievals, we're doing a very similar thing. But in other cases, we're getting much more absorbing scene.
I'm sorry, I don't understand. So the green dots should be reality or closest measurements, right?
Correct.
So both of the others are pretty off.
Well, one is more off than the other, let's put it that way. If you look at the error bars from a retrieval, in this case, the ones up here are an overestimate, but they agree within the uncertainties for those observations.
All the down, all the
But these down here, this set down here, are very different, and they're outside of the error bar, assessed errors. So what seems to be happening is that in some of our observations, when we're not using the LiDAR, we're retrieving to a scene where we're getting the same optical depth as our observation, and we're getting the same optical depth as if we use a LiDAR. But the amount of absorption is completely different. And it almost seems like we're coming to a false minima in terms of our observation. We're coming to a match that is not the best. representation of what's actually there.
Does this imply, sorry, just out of curiosity, that the measurements have almost no error associated with them? That you can measure the single scattering albedo very precisely in situ?
Okay, these actually do have error bars associated with them. So the optical depth is very, very accurate from the summatometer on the ground. These don't have an error bar because at the time I made this plot, I didn't have error bars from them. Now they are about this.
They're kind of big, yeah.
Yeah, they're big. It's been a little bit troublesome because the particular instrument that I'm using that's made a 20% change in their absorption coefficient observations, and that happened in December. So in the end, however, it actually made things a little bit closer to our observations, and yeah, their errors are sort of like they're about the same as ours, which are still pretty high.
You know, at the first plot you have the plume in that area, but you don't see that in the single scattering of the optical signals. Or is that not the same x-axis?
In which area? So this is all the plume right here. The point, if you look at, say, these values here, the inherent optical properties of those aerosols are not changing much across the plume. There might be more aerosols in some part of the plume and less in another part, and that's why it's different here as opposed to here. But it's, in fact, it's not that much different because you can see the optical depth is a whole lot higher here than it is here. It's kind of
So that's all.
This is all plume right here. Yeah. So, but the point that we wanted to make was that we expect the optical depth to be varying throughout the plume. You know, it's a very recent plume. There's lots of shape effects, but the chemistry that goes into making it are not changing as rapidly. That's sort of one of the assumptions that we have. So the question is, why does this happen, and why does it happen for only some aerosols, and or some of our retrievals, not all of them? It sort of seems to be random. Oh, I'm sorry, this didn't come up very well, but this is the size distributions that we retrieved compared to the in situ observations of size. So the solid line here is the in situ observation from the aircraft. The dashed line, which is this guy right here, is the sort of average size distribution we found when we were not using the LiDAR information. The dashed dot line is what we found when we are using the LiDAR information. So what seems to be happening here is that we're agreeing very, very well for certain sizes, like this. And we're matching the observations very, very well. It's just other sizes, especially small radius particles, that it doesn't seem to be constrained at all by our observations. And so the point here is that with and without the LiDAR information, we were able to come up with a size distribution that plausibly fit our observations for these sizes. And at other sizes, it didn't fit that well because there was no information in our observations to constrain that. Because of this difference in the fit, the model then had to compensate and change the amount of absorption, which is why there's such a difference between the two. So the way I'm sort of interpreting it is this: about half of the retrievals without the HSRL data, the LiDAR data, converge to what I'm calling a false minima. This minima is expressed in a fine mode size and refractive index, but it's not expressed in terms of optical depth. Optical depth is sort of insensitive to these differences. So successful retrievals without the HSRL data are very similar to the HSRL retrieved results. So that basically tells us that you know, in some cases we did find a right solution, in some cases we didn't. So the actual information about the size distribution, or I'm sorry, the vertical distribution of the aerosols is not as important as just starting close to the actual solution. So the initial number concentration estimates, the initial estimate of the optical depth, which is what we also use from the LiDAR, is what's most important. vertical distribution is less so. Furthermore, okay, some other things. There's a large optical thickness error, especially despite some of the similarity in results. And this is the motivation for some of the changes that I made in the next set of retrievals. So, the second case study I looked at was the ability to retrieve aerosols over clouds. Typically, for aerosols over clouds, it's not the type of, we don't have a lot of observations of aerosol optical properties over clouds. But it's a potentially important scenario from a climatological point of view. There's a couple places in the world where there's sort of persistent marine stratocumulus clouds. Absorbing aerosols from biomass burning tend to blow out over these clouds. And if they're on a layer above them, there's a potential direct effect of those aerosols. Most aerosol retrieval algorithms from Modis or whatever do not work to simultaneously retrieve aerosol and cloud properties. So we wanted to see, well, can we do this? And our motivation was from a study using Polder by Levenberg-Marquardt. You may remember him, he was a postdoc here a couple of years ago. And so he looked at Polder and tried to do the same sort of thing. But Polder has a much more limited angular resolution than we do with RSP. So we said, well, maybe we can do it even better. So we took data from a scene from the Milagro field campaign. Milagro is a megacity initiative, local and global research observations. We were based in central Mexico in April and March of 2006. This time we were on a different airplane, the Jetstream 31. This is where the RSP was located, which was once the toilet of the airplane. Now there's a bucket. So this is our scene. We're based in Veracruz down here. This is the Gulf of Mexico. Mexico City is this valley in here. So in this particular day, earlier on in the morning, there was a whole bunch of marine stratocumulus clouds present over the Gulf. They were in the process of dissipating. At the time that we flew over this cloud, there's only a little bit left right here. So this yellow line is our flight track, or a portion of our flight track. The blue area is where we're looking. So the scene that I'm observing is right here. Now, for various reasons, we believe that there were a layer of aerosols on top of this cloud right here. And so we wanted to try to retrieve aerosol properties in that scene. Now the question here, the problem is that on this particular field campaign, we didn't have the luxury of having a LiDAR with us. So we don't have a direct observation of the vertical distribution of the aerosols. This little squiggly here was later on that the aircraft which overflew the cloud then spiraled down to the surface. And during that spiral, assuming that the meteorological conditions are pretty similar here, this is where our cloud once was, we have a profile of temperature and we have a profile of aerosol optical depth from a sun photometer on board the aircraft. So we think we have vertical distributions that we observed here that are applicable here. I mean, sort of this. So in this area where we circled down to the surface in the absence of the cloud, this is the green line here is a temperature that was observed. The black line here is a change in aerosol optical depth. So where this is high, that means there's a lot of aerosols at that particular height. So there's sort of two layers here. One was within a cloud. We took this inversion here to be the cloud top height, and we modeled it like this. We said, okay, clouds are this high, aerosols are this high. What can we do? So then the question is, why do we think that we can retrieve aerosol properties above clouds? So this is a simulation of what we expect to see in this scenario. This is for, well, if you look at the black line here, it's a cloud with a sort of a marine stratocumulus cloud, so relatively small effective radius, with nothing above it. And you can see that this is Q reflectance is a function of scattering angle. This very strong feature here is the rainbow. So the location in terms of angle of this peak here tells us a lot about the type of cloud droplets that are reflecting there. So this location tells us essentially the size of the particles that are present in the cloud. Whereas over here, you can see these other simulations. I put things like aerosols on top, or I change the aerosol height. And so other parameters are expressed at these angles right here. Essentially, we think there's information about aerosol properties and cloud top height from these scattered angles. Therefore, if we can specify what the cloud top height is externally, we can then hopefully retrieve the aerosol properties. And then from the location of this peak over here, we hope to retrieve cloud droplet size. So this is why we think in a sort of qualitative sense that our observations are independent, or independently able to retrieve those parameters. But that's qualitative, and there is actually a more quantitative way we can look at this. To go back to the Jacobian matrix that I described before, we can compute what we expect a model or a sensitivity to changes in various parameters using a model. So we use our simulation to project. We can then use that to project our expected observational error to come up with an expected retrieval error in different scenarios. So then what we can do is play around with things. Okay, well, let's look at a Jacobian for a particular type of scene, and what we expect our observation to be. Can we retrieve various parameters within the uncertainties that we expect to see? And so this helps us choose the sort of best retrieval strategy. You know, if we do this and we see that our simulated error for a particular parameter is very, very large, well, maybe we'll just constrain that and not allow it to vary. In which case, we try to reduce the amount of correlations between our different parameters that we're retrieving. So this is an example of doing that sort of thing. Oh, I should say, by the way, I mentioned before that there's a paper by Levenberg-Marquardt who looked at polar data to try to use this sort of thing. Now, polar doesn't have the sort of angular sampling resolution that we do with RSP. So polar is not able to come up with this cloud droplet size because they can't identify this the location of this peak in a very accurate way. So what he was forced to do was to look only at these angles over here. And so what I wanted to do then is say, all right, is it better for us to use all of the data here or just this data over here to retrieve aerosol properties? So using this technique, this is the sort of results that I found. This is the simulated error for a variety of optical depths. This is the error in terms of optical depth and error in terms of fine mode effective radius. The black line is for retrievals using all of the observation angles. The dashed line is for retrievals just using the side scattering angles. And you can see that for us, it actually makes much more sense to use all of the observational angles. And this applies both in terms of fine mode optical depth and in terms of effective radius. This little dotted line in here is the threshold that Michael Mishenko established in this paper here. These are sort of the observational goals of the GLORY, the APS and GLORY, for doing retrievals of aerosols over land. So this is not for aerosols over land, but just in a comparison of what we can do. And so in this case, we think we can do just as well in terms of optical depth over land. This dotted line on here would be way up here, so we can also retrieve effective radius very well, we think. If we look, however, in terms of refractive index, we don't do as well. I mean, certainly it is better to use all the different observation angles, like we said before. But you can see that we don't meet these thresholds unless our optical depth is very, very high. And the probability of getting optical depths this high is quite low, so most of our optical depths are going to be down here. So what this is telling us then is that we think in this sort of scenario, we can retrieve optical depth and size of the aerosols just as well as we can over land or over water. But in terms of real refractive index or the quantity of absorption, we can do something, but it's not nearly as accurate as what we'd be able to do over land. So that's a simulation.
Well, can you, what's the significance of the threshold? Surely some information is always better than no information.
True, but if you have two, okay, so what I didn't say and what's an issue here is that this is just talking about information that is present within the model. It doesn't talk about the correlations between different parameters. So if you have highly variable parameters and high correlations with other parameters, if we allow something like this to vary, that can translate into errors in the other parameters that are also being retrieved. So in some cases, it makes more sense to nail down something like this and not allow this as sort of a free parameter that can go anywhere, and because of the correlations with other parameters, affect retrievals in other parameters.
Right, but for any retrieval of a particular scene, there's going to be an error matrix which is not going to be uniform in each of the individual parameters independently, right?
Of course,
so,
yeah.
you know, so what you're going to constrain is some space, and then your error bar is going to be somewhere around here, right?
Mm-hmm.
So why not just do that? That's still useful information.
It is, but it's a little bit easier to express it in terms of just an individual and not have to talk about the correlations between them. In any case, in the retrievals that I do actually retrieve these parameters. But in terms of trying to meet the criteria established in this paper,
Yeah. So why are there any criteria? What's the criteria for?
I believe
Aerosol direct forcing. I think it's something like a quarter of 1 square meter at a certain time. I'm not certain, but it had to do with climate forcing. In order to be able to see some changes over, in order to monitor a change in climate forcing caused by aerosols of a certain amount, they calculated what the corresponding threshold was in the optical.
Well, that's not the same thing as what you're doing. You're just trying to tell me what kind of aerosols there are now. That's not the same as being able to detect the climate forcing over the lifetime of the instrument.
No, but I guess that maybe, well, my feeling is that if you have a continuous record after the APS, another instrument, another polarimeter that continues this kind of observations, then you start to establish trends.
Oh, right, yeah, of course.
I mean,
But I mean, I think my point was that, but that depends on what your signal is. If your signal is the long-term change in radiative forcing, well, that's one signal, but that might not be the signal you're only interested in.
But
This is not that.
But look at it this way. So the errors I'm assessing in terms of signal scattering albedo is a value between 0 and 1,
Right.
and these errors are 0.5.
Okay, well, obviously that's not very useful.
Yeah, it's a total jump.
But you know, down here you got 0.1 and the error is
Right,
0.05.
right,
Well, you know what, that's not terrible.
It's not. But I just want to give some sort of baseline in comparison to how well we can do in other scenarios. How well can we do in this aerosol over cloud compared to how well we think we can do in other parts of the
Right. I mean, I just wouldn't want you to be throwing away data that could be useful for somebody at some point, because there's some kind of arbitrary threshold of
Sure, but I wanted to have some means to put it in context.
Right.
So, and just to say that this is not very useful at all. So, and like I was saying, this does not include correlation between parameters, which can also hinder accurate retrievals. Some of the other things I did in the paper was to look at correlations. So, for example, the imaginary refractive index and the cloud effective variance are highly correlated. So, if you think you can have a better estimate for what this is, then you're not going to affect your retrieval of effective variance, for example. So, moving on to retrieval of the actual data, I'm using now 7 channels. I'm using the 2250. I'm not using the total reflectance like before. I'm just using polarized reflectance. Probably the same number of observations, 525. Like I said before, we've assumed something about the vertical distribution of the clouds and aerosols. And we're starting with these sort of sets of aerosols right here. This is from climatology, from the AirNet symptometer network, basically Mexico City urban industrial mix. So this is our match to our observations. The observations are solid lines. Our model is dashed lines. And you can see that's not a perfect match. We actually don't do very well in the rainbow right here, but we do seem to have a very close match at these side scattering angles where we think aerosol properties are most important. In terms of the retrieve parameters, this is what we're getting. So this is a relatively small droplet-sized cloud, a relatively small amount of imaginary refractive index, general size aerosols, and an optical depth of 0.1 at 532 nanometers. And just as we expected from our simulations, we have very large values in imaginary refractive index, which is the same thing as saying we have very large uncertainties in terms of the single scattering albedo. So this is, I mean, single scattering albedo is between 0 and 1, and it's 0.45, so it's not a very useful measurement. However, we can also compare our results to what was observed in the scene. This is our comparison of optical depth in black to the suntotometer in green here, and you can see it's kind of faint, but there's error bars associated with this, and they agree very, very well at all different wavelengths. So that's very encouraging. And then actually, there is some observations of single scattering albedo, of the absorption of aerosols from an instrument called the Solar Spectral Flux Radiometer. This is a relatively new technique for them, and they have relatively large errors. But you can see here their values are in red. This is a function of wavelength. Our retrievals are this black line right here. Now, I didn't put error bars on our retrievals because they'd just be off the whole plot here. But we actually do agree within the error bars of the other technique. It's more reasonable than the actual retrieval uncertainties would suggest. So that's somewhat encouraging. There is always the possibility that our error covariance matrix does not adequately represent what's going on in the scene, and we could be overestimating the amount of error that we expect to be seeing. So, the way I'm interpreting this is that fine mode aerosol optical depth and size distribution are retrieved accurately as we predicted with our simulations. The fine mode complex refractive index, or imaginary refractive index, I should say, related single scattering albedo have large assessed errors, but this is similar to other observations. So provided that cloud top height is known, we think that we can at least retrieve some information about aerosols lofted above clouds, and this would be something that APS would be able to do that really hasn't been done much at all in the past. The only things that have been done have been with LiDARs in the past. So we can come up with some information. Unfortunately, it's we really want to know the absorption, and we don't think we can do as well with that as we would really like. So, just to sort of wrap up everything, I hope by now you understand the climate community needs accurate remote sensing of aerosols, scanning polarimeters such as the RSP, will promise for aerosol optical property retrieval, but also it's still, there's a lot of issues to be resolved, and there's still a lot of complications that we need to worry about. So as what I've done as part of my thesis is I made this testing software, DAO, and I've come up with sort of a means to test the capability of DAO to determine retrieval capability in several different scenarios, typically looking at scenarios that we're calling difficult. And that's essentially it. I want to list all of the collaborators for the two papers that I described here. They're here, some of them are here, some of them are at NASA Ames, some are at NASA Langley, and a variety of other places. I should also say that I was funded by the NSF for the first 2 years of graduate school and by Hillary subsequently. And then, so the other thing we're supposed to do is play the video of the launch today. And of course, the launch was at 2 in the morning, so I don't know how it's so sunny, but